So you two guys decided what topic?
Yeah.
What are you going to write down?
Superfluid.
What's that?
Superfluid.
Super.
Yeah.
Superfluidity.
Helium magical. Low temperature.
That's
Oh, maybe too out there.
yeah.
Uh,
That's okay. Yeah. This is mostly about the Bose-Einstein condensation, right?
Yeah.
I like more like some technique development.
Okay.
Yeah.
Then I will figure out next.
Yeah. How about you?
I'm thinking about sputtering.
Yeah. Okay. Oh, but what means somebody else is going to do vacuum systems, right?
Ecosystem.
Okay. Yeah, that should be fine.
I'm also thinking about
I want something like a real, like you are doing CVD. That's something you are doing, right?
yeah.
Yeah.
I'm thinking about also microscopy.
Okay. Yeah, that's
electron
fine. Yeah,
microscopy.
that's, he's doing non-electron microscopy, right?
Ansaka?
Ansaka is going.
Yeah,
And Isunanga is doing a vacuum system.
vacuum system.
Yeah.
You
Do
can
Do the AFM, Rishi.
Yeah.
If you do AFM, then you can talk about the superfluids, because then somehow you'll figure a way to tie them together.
Superfluid with the.
yeah. You can rope it together and like.
So,
So how was, did you start working today? Did you?
Yeah, yesterday I did.
Oh, yesterday.
Yes,
Oh, you did over there?
yeah.
Oh, you should start doing it here. Every day you have to go there.
Yeah, no,
I
like
think-
we have to wait 3 days for light.
You have to do it here, in this lab, in this building, yeah. You cannot go every day over there, right?
Ah.
We have everything here. I will talk to Milinda,
Okay.
yeah.
okay, Ansaka, you will present TEM or SM, electron microscopy?
My presentation,
Yeah.
I am TM,
TEM, SM.
Hmm.
What's that?
TM, SCM, yeah.
And SCM both?
Yeah, 30% thing, yeah.
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 So these are the electron microscopy tools.
Yeah.
basically.
Yeah.
So, like he said, maybe you can do STM, AFM, something like that. Yeah. But
Okay.
what else, so I discuss those things here.
Okay. I have to discuss the advantages, disadvantages, contrast.
Okay, okay.
Well, I'm doing ramen scattering. Or ramen systems.
Okay, I will again go through whole course and I will figure out one interesting topic.
Yeah.
You have to write a
Like-
small
Yeah,
report.
yeah,
Something
you have to
from
write
deposition.
also, yeah.
Sputtering is quite easy.
Sputtering, yeah, sputtering, that means you are going to cover everything like DC, AC,
DC.
reactive sputtering, everything.
In 5 minutes?
Yeah. What is, I mean, if you say sputtering, there's only one sputtering, right?
Yeah.
But what I want is something that you will do in a lab, right? At least, yeah, like he's talking about CMBT, and that's good, right?
Yeah.
Yeah, you can talk about sputtering DC, AC, reactive, ion sputtering, things like that, yeah, few things, yeah. I don't say 5 to 10 minutes, yeah, so 5 minutes, what can you say, right?
That's just the introduction.
Yeah, that's all you can, but thing is, I have introduced everything here. We are not going to say the same thing. Where's Isunanga today?
Can I give a call?
Yeah,
He was here.
he was here?
He was here once upon a time.
Look, I will call.
Can call from here.
It's like a quantum, you know. It's like maybe there.
Superposition.
Yeah, yeah.
No.
I think I can quickly go ahead and finish this job today, so then maybe Tuesday we can do the microfracture.
Okay.
Yeah, he's on the way.
Forget?
I think think we were all just early today.
Oh,
You think so?
yeah. Yeah,
What's the
no.
time now? I forgot. myself.
5:29.
Oh, still not 30. Oh, that's strange,
Yeah.
Usually these two guys come little late.
Well, we were all together, and I was like, all right, let's go.
They're studying for the quals.
We are here from the morning today, so.
So you all, except you, all four are doing
Well,
Second?
this Saturday also?
No.
You,
they were just with me for
you
emotional
you pass
support.
both
Yeah.
Yeah.
thermal and
Yeah.
quantum. You both?
Yeah.
Okay, you are done.
It's Ranga. He came in here, he's like, why are you calling me? I'm not even late.
Yeah. He came on time. Okay, then let's get started. So today we are going to mostly talk about this different atom or molecular vibrations. Atoms can vibrate, right? So you need to have two atoms at least, right? So typically vibrations we are talking about something attached with the spring, right? So then also they can rotate, right? So they can do both vibration and rotation. So then most of the time, even if you have single atom, you can have excited states, right? So then you can see a spectroscopy just by exciting it to a higher level or by moving it from high level to lower level, then it emits photons and things like that, right? So this basically we are going to talk about these things, so I will go in details. So these are the three things, right? It can be vibrational energies, so it can be rotational, or it can have vibration, rotation, both. So then mostly this excitation, right? So energy states can excite, and maybe relaxation from the excited states. That's why you see the most of the spectroscopy coming, right? So one is this UV spectroscopy. So this is the most common, most easiest, and I think for chemists, this is the spectrometer. This basically, you have simple, that we talk about the spectrometer, right? It has light coming in, then you have one mirror to reflect it, then you have a diffraction grating, so that will disperse the light. So then another mirror, so eventually it goes to the photodetector, right? So then we have the sample somewhere, it will absorb light. Then you can, since diffraction grating is split into different wavelengths, right? Then you can see what different wavelengths. So typically, if you are talking about UVs, you can look at the absorption. So if you have semiconductor, absorption can come from basically from, if you have everybody familiar with the valence and conduction band, right? So if you can have some absorption if you can excite electron from valence band to conduction band, right? So that will show up in your the spectrometer, because you are changing your energy, right? From here, or sometimes you can have this something called the defect levels. So then you can have some electron exciting from here, or maybe some holes coming here, something called the acceptor levels, and those kind of things show up in UVBs. But if you have a simple molecule, so mostly you can see that one from these simple excitations. I think we know, not the electronic excitation. There are a few things. Electronic excitation means where you have these quantum states, right? You have ground state and all these other electronic states. But you can have a molecular states. I think everybody familiar with this sigma and pi bonding. So typically, if you sigma bonds are if you have something like if you take two, say p orbitals. Typically, s orbitals are spherical symmetric, right? P orbitals you have this kind of shape. If you have two p orbitals, if you overlap sideways, they make something called the sigma orbitals, right? But if they have these p orbitals like this, so here you can make the pi orbitals, right? So then also you can have non-bondings, and also I think in quantum mechanics we talk about bonding and anti-bonding. If we have two atoms together, right, to make a molecule. So for example, hydrogen molecule, basically you are having one hydrogen and another hydrogen state, right? So when you bring these two together, so this one has only one electron, right? So this one also has one electron. So when you bring together, then you can have this kind, these two can combine, right? So, or you can have something that doesn't really bond. So then we call it we call the bonding state, because they bond together. So this is anti-bonding, right? So they don't really make that. So if you look at these things together, how does that look like? If you have some hydrogen has this orbital, right? This one also has s orbital. When they come together, you can have these two coming together and making this your electron concentration is really centered here, right? So, but antibonding means they don't make the real bond, so it's more like something like this. You have zero electron density here. Here you have electron density concentrated here, right? That's why you make the bonding. Here you don't make the bonding, right? So here actually your electron concentration is zero, right? Actually this looks something like this, right? So that's the anti-bonding situation. If you think about in wave function, how do they look like? So if you have one wave function like this, and another wave function for this one hydrogen, so this is other hydrogen. Bonding means they overlap so that you have, so these two, right? So antibonding means, actually this is symmetry. Antibonding means they bonding like this, so then this one is becoming like this. So that means you have some place the electron density is zero. That's where this somewhere here. But in this case, you can see they are becoming. How do I say? Actually, this is not a good picture. So actually, if you add these two, they become more like this one, right? Both coming together. So this is where you get the largest concentration. That's the wave function picture. So the bonding means actually it becomes more like a symmetric wave function. So in this case, it becomes more like a antisymmetric, right? These are the basic things. So what I want to say is these things you can really study from this UV spectroscopy. So if you have some chemical, if you use the benzene or something, right? So you can easily look at typically if you have this energy, antibonding has high energy, right? So compared to the bonding states, so you have this sigma bonding, pi bonding, this is sigma non-bonding, so antibonding, and pi antibonding. That's a star means antibonding situation. So then you have something called, they don't make the real bond. The atoms will stay as it is, but they are still in close vicinity, but they don't make the bonding like in the other case. So then you can have these different transitions, right? From sigma to sigma star, or pi to pi star, or n to pi star, like this kind of. So these things can be easily seen from your UV spectrometer. So if you put this one, you will see like this is for, I don't know, whatever that. So this is something you are seeing like 250, and this is something, 500 something. This you can easily relate to this kind of transitions. So these are molecular states, right? Not the electronic states what you see in like semiconductors. So these are molecular states. So you can see if you take different molecule like methane, you have these vibrations happening around like 122 nanometer wavelength. So then if you take, so actually one thing, if you look at the UV spectrometers, typically your energy axis is given in lambda, please remember, so not centimeter inverse. Most of the UV spectrometers, your x-axis is given in lambda. That means this is high energy, right? Low lambda, this is iodine. So you can see this methane. So each molecule has its own characteristic, this peak. So that's how you identify if you have certain element, something that you don't know. So you can just do this UVVs, and depending on that wavelength, you can identify what that molecule is. That's pretty straightforward. Yeah.
That is then Electria, localization, plasma.
No, that's to have a plasmon, you have to have a solid surface, right? You need to have a lot of electrons. Plasmon means electron oscillations, right? So that's if you have a like nanoparticle, gold nanoparticle or something, then you have a lot of electrons there. Then photons will couple with that electron, then it will make these electrons to oscillate. So then you have something called the plasmon frequency, usually given by something Ne squared divided by something, I don't know, M something, right? So that depends on your electron density and the mass. That's if we have a solid surface. I'm here talking about just simple molecules, methane or acetylene, or, yeah.
I was actually talking about the plasmons
Yeah.
with Dr. Mendez today.
Yeah.
So, Anshaka, if you're interested, like one of the coming labs for the optics.
Oh, about the
doing
plasmons,
the
yeah.
plasmons.
So they put maybe gold film or something?
Yeah, and then
Yeah.
shine the laser
Like,
on
yeah,
it.
so to have a plasmon, you need to have a lot of free electrons, right? That you can get from like any metal. Typically, you get very good plasmon from silver particles, even
Same.
so, even gold, platinum, those things. Yeah. So this is slightly different, but you can identify plasmons from these UVVs. So that's really interesting because depending on the nanoparticle size, your plasmon peak is going to be broadened. So also there will be some shift here. So from that you can see whether your nanoparticles are like 1 nanometer or 10 nanometers. So, because it's a size dependent property, right, plasmons. So here I'm talking about this. I think the UVVC is very simple, and there's no sample preparation. You need to, there's something called the cuvette. You just put your sample here and put it in the beam. But when you do that one, typically most of the UV spectrometers have dual beam. That means your beam is going in these two different ways. This is your sample. So then you have reference one. So if you're doing something, then first you put the cuvette without anything here. Then you have the cuvette with the sample. Then you can take the ratio. So that's how you take care of the background. Otherwise, you will have a lot of absorption from your cuvette walls and other things, right? So also, if you want some particle, so you have solid particles, if you dissolve it in some solution, then first you do it with just the solution. Other one is the particle dissolved in the solution. So that is your background, right? So that's how you get the information about your particles. Most of the UVVs are dual beam. So if you don't have dual beam, you just put one first, take the spectrum and save it like the reference, then you put the second one and take the ratio. So that's depending on modern spectrometers are their dual beam. You just put the two together and so then next thing is a very similar thing. If you want to look at any these chemicals, the infrared spectroscopy. This is also very simple. So just similar spectrometer. So you have the same similar dispersive things. But here you are looking at the wave numbers. So this is centimeter inverse, right? Mostly like very large. That means very large. Centimeter inverse, right? So this is, that means in the infrared or far infrared region. So, but later I will show you this IR and Raman, they both are very complementary. So you can confirm some information, what you gather from IR with Raman. But later we'll talk a little bit. There's something called the selection rules. Not all the transitions or states, they are Raman active or IR active. There are certain forbidden ones. So in that case, maybe Raman might give you a signal, but FTIR might not give you. Sorry, IR. Right now I say IR. IR is the old technique, so just simple spectrometers. Nowadays, most of the IR spectrometers are FTIR. That means Fourier transform IR. That means you collect your data at once as a function of time, then you do the Fourier transform to get the frequency, right? Fourier transform, everybody family, right? From time domain to frequency domain. So, but old days, all these spectrometers, they just do like sweep lambda and collect this one. But that is a little slow. FTIR, you just take a very short period of time and immediately do the Fourier transform to get that one. That's what most of the novel. So you can see molecule energies, they can have different these vibrations, right? So typically we call these symmetrically stretching, both symmetry or asymmetric stretching. When this is going down, this is going up, or this is scissoring, so more like scissor, right? Like this kind of thing. Or you can have this rocking chair, right? Going this way, and this waggling and wagging, different things can happen, right? Because molecules can vibrate in different ways, right? So they all can be looked at by IR spectroscopy. This is a very simple technique. Also, if you look at your energy ranges, typically we see very longer wavelength. That means IR kind of range. Mostly you are seeing the rotational vibrators, rotational motion, right? So, because we know like water molecule that can have rotational symmetry. So microwave frequencies are common for rotational molecules. So then you can have vibrational ones. So they are mostly can be IR to visible light. So then ultraviolet means mostly if you have some molecule, these are very high energy, right? If your molecule can be dissociated. So to dissociate a molecule, you need very high energy, right? Like when Zen is doing methane experiments, he's heating it to like 1200 C to break methane molecule into carbon and hydrogen, right? Or he can use lower temperature and use a plasma. So that those things will provide you UV kind, because that's a very large energy, right? Those scales I think important to know.
What's the energy scale to get the electron from the valence to the vacuum?
Valence to, you mean, first it has to come to conduction band, right?
Yeah.
From conduction band, it will be the work function. So valence band to conduction band, you have to overcome the band gap. So once it is in the conduction band, so then you need to overcome the work function.
That's weird.
Typical work function are several electron volts, right? So then the band gap, depending on if you have a silicon, it's only like 0.5 or 0.6 electron volt. But if you have gallium nitride, that's like 3 electron volts, right? Depending on the semiconductor.
What is the approximate electron volt in inverse centimeters?
Yeah, I gave you that here.
Conversion?
Yeah, conversion table, I gave that table.
I think
Yeah. Here is typical electron volts. In micrometers, is this a number you need to remember? So if you have 1 micrometer, this is more like infrared, right? 1 point, because 1 micrometer means 1000 nanometers. That is in the infrared region. So actually far infrared, right?
Yeah.
So that is 1 electron volt. Yeah. This is the number everybody should remember.
Okay.
Whatever, even if you are doing any other area, 1 electron volt is 1.23 micrometers. This is something everybody should know. So if you are in 1.23 is enough to remember. Yeah, so like I said, this is the old simple IR spectrometers, just like before you have IR source, sample and the reference, then you get this one and go through detectors and processors and everything. So you can see, typically if you look at the IR spectrometers, this is in centimeter inverse. So this is increase in this way, that means your energy is increasing this way, right? So this is 1000, 2000, like this. Please remember, this is energy. Centimeter inverse means energy unit, right? So energy is increasing this way. You can see mostly the single bond, like carbon. If you have, like single carbon bond, like if you have polymer something, or something that has only one bond here. So those carbon bond, because then you have other bonds to satisfy all this, but they all have one single bond. So they have these characteristic frequencies in this very small energy, like 1000 to maybe 1500 region here. But if we have something that have double bonds, like even in methane, right, you have. So if you have any double bond, their energies are 1500 to about 1800. So if you have like triple bonds, like carbon-carbon, so then you can have, so they are much large energy. So these are all about carbon-carbon or carbon-nitrogen. But if you have hydrocarbons, like methane has carbon-hydrogen bonds, right, these ones. If you have any hydrogen carbon bond, typical energies are in this range. So if we have other bonds like this NH or OH, they are even higher. So from here you can easily tell you what kind of bonds you have, right? So if you put your material in the IR spectrometer, actually one thing is IR spectrometer is very difficult to analyze, because you see hundreds of peaks, because all the these attached molecules will show up there, right? So it's not like Raman. Raman we have very distinct few, but IR is really dense. Yeah, let me show one of the typical IR spectrometers are like this. You can see this is not too bad, right? Like I said, you will see like low frequency. That's also increasing this way. CH2, they are more like double bonds, so then we here. So then also depending on this stretching modes, right? So here is a double bond here. Like remember, asymmetric stretching, one goes this way, other one goes this way. So you can identify this is not bad actually. So most of the time if you look at IR, they have hundreds of these absorption peaks. This is actually transmission. So anyway, that's so. Then we talked about at low energy vibrations. You can have rotational and vibrational states, right? Rotational means usually is given by if you take a simple rotor. So what is the energy? You know the using simple energy, usually half I omega squared kind of thing, right? It's a rotational motion. So if you quantize that one, typically I is more like the moment of inertia, right? So your energies are given like, still it is quantized, Jj plus 1.
Right.
So then vibrational one simply simple harmonic oscillator, right? This one, this is typically half k x squared kind of thing. So that's then you have this is something called the, I don't know the family, something called the zero. What do you call it? Even at 0 Kelvin, you have some intrinsic this vibration. So that's what this half is coming from here. So this new, depending on your 1, 2, 3, like that. So this is typically quantized in units of this h, because this is mostly what we call the phonons. So later we'll talk about that one. Any oscillations, right? So that will actually, oscillation is something that propagate along the material, right? That you can define as a wave, right? This, if you look at each molecule atom, like I said, they can be modeled as these atoms attached by some springs, right? So the springs are moving. So then, if you look at the entire solid, this motion will look like something moving wave. Like if you take a string of here, so if you attach both ends, if you plug this one, what will happen? The molecules will move up and down. But if you look, what do you see? You see some traveling wave, right? Exactly like this here, these molecules are vibrating about this equilibrium position. But it will, you see this one as a moving wave. So that wave we talk something like, something called a phonon. Phonon is basically wave. So that represents these oscillations, right? So that phonon has a this energy given by h nu or h cross omega. So that, but this is in quantum mechanically we write this one as some number times this one, right? So you have 1 phonon, 2 phonon, like that. But even at 0 Kelvin, so these molecules won't be perfectly stationary. They have a 0 point motion. This half is coming from the 0 point. 0 point means even at 0 Kelvin, they are not stationary. That's called the 0 point. That's what this mu plus half. So mu can be any number, right? But they have to be integer numbers. So these are the vibrational energy states. You can see depending on this mu, you can, this is one quantum of phonon. So then you can have 1, 2, 3 like that, right? These are how we go. So then you can have similar thing for Ej. These are rotational states. So that's how we write this one. If you take one vibrational state, then you can have a bunch of this rotational state for that one. So if you go to another vibrational state, you can have a bunch of rotational states. So this nu represents each vibrational mode. So here nu equals 0, 1, like that. For each this vibrational mode, you will have a bunch of this J values coming, J1, 0, 1, 2, 3, like that. So these are the vibrational states, these are the rotational states. So then you can have transitions from this vibration to vibration, that is basically phonons, right? So then you can have rotational energies from these transitions. So then typically people, you can see how it's done. So this is both rotational and vibrational. So in the rotational state, if you have something that has this delta J from one to another one, if they are +1, we call that is a R branch. If that is a -1, we call it a free branch, depending on. So this, if you have some molecules, they have both rotational and vibration, you see lot of small peaks corresponding to these values. But remember, these ones coming in like microwave frequencies, right? The rotational ones come in the microwave frequencies down to maybe UV. Yeah. So like I said, this is nowadays, like I said, most of the spectrometers are Fourier transform, right? So in this case, basically that's a simple Michelson interferometer. You have these two mirrors, then you have your light source, then we know this is a mirror and the beam splitter, right? You can have one partial light going from here, then they come here and they interfere here, right? You can get the interference. So everybody, and the Michelson interferometer. That's what they use in the LEGO, right? That's for the gravitational waves.
Mm-hmm.
In that case, they have these paths like kilometers long, right? To observe that any gravitational waves coming from this supernova explosion or collision of these two galaxies. So they can see any small change here due to that gravitational wave. So that can be detected here, right? So similar thing here, but here you can have this moving mirror. By moving mirror, what we do? We change the path difference, right? So that will give the phase difference, that will give you the constructive or destructive interference. That's how you look at this one. So you just put the sample and see. So in this case, you just directly collect your data as a function of time very quickly, then you do the Fourier transform. Everyone knows how to go from time domain to frequency domain, right? If you need something in frequency, typically we do whatever your function is, suppose something that has function in t, I need something in function of frequency, right? So then you have to do like e minus I omega t. This has to be in e, right? So when you integrate this one, everything comes in unit of omega, right? So that's how you do from time domain to frequency domain. First you collect this data using that Michelson interferometer, then the software will do the frequency domain transformation. That's pretty straightforward. Very fast, this one. So when you do this one, you know how to add the two wave functions, right? That's where you get these beats and those are details. If somebody wants to talk about this one, that's what I like to say. Give more details about these things. I can just give you the basic, right? So if you do that one, yeah. So this is where you get this is where the time domain to frequency domain, right? That was explained. So then your spectrum would be something like this. You can see all these. You can identify. You need to look at these tables, right? So if you have double bonds, so we know where those energies are coming, and also look at whether they are stretching modes or things. It's little difficult. You have to sit down and identify all these fields. FTI, any IR spectrum or spectra are kind of difficult to analyze because they are so rich. So then I will talk about next one is Raman spectroscopy. So this is what we mostly use here. That's also very quick method. When we make a sample, immediately go to the Raman spectrometer. It's 5 minutes, maybe 10 minutes, right, maximum. We can quickly get the, if you are good user.
Well, our machine sometimes, it takes a while to boot up.
Yeah. Oh, you mean that's yeah. So if you have a good working spectrometer, it's only 5 minutes. So Raman basic is you shine laser light. So then you expect some vibrations or whatever happening in the sample. So that will absorb that light, so then outcoming light has low energy, right? So that's pretty much, by measuring the difference between these two wavelengths, you can get the difference. That difference will be equal to whatever the sample was doing. It can be phonon, or it can be creation of phonon, or annihilation of phonon, or it can be other vibrations. So whatever happening.
That's for Stokes shift,
What's
right?
that?
That's for Stokes shift.
Yeah, yeah.
Right, where it
So
loses
let me
energy.
explain that one. So typically, yeah. So,
Oh.
but in our one, we are mostly doing the Stokes one. So usually, if you think about this one, suppose your material is at certain energy state here. So then suppose this is my excited state. So now if I have this laser coming with some frequency, suppose if I use, you are using like 632 nanometer laser, the red light. So then this will excite it to some virtual state here. So now this can decay down to this original one. So in this case, nothing happens, right? You have the same energy as it is, outcome energy also h nu 0, right? If you have the same energy going from here to here, if it comes back to same one, there's no difference, right? So that means we call this a Rayleigh scattering. That means your incoming energy and the outcome energy both are the same. So that means you will see very strong peak with no change in your energy. That's elastic scattering, right? But if you have, suppose this is your excited state. So if I excite here, but then it only comes down to this energy, that means outgoing energy has little less energy, right, coming down. This much is missing. I call this is h cross omega. So yeah, so this is h cross. If I put h cross, that means should be omega, right? H means you have to have nu, right? 2 pi is there, doesn't matter. So that means outgoing light has low energy, right? Low energy means longer wavelength. So we call then whatever outgoing one has say h nu prime. So this is equal to really h nu, that incoming one minus this one, right? So that's why, because this is what sample is doing. So this is what we are measuring, right? Because we know this one, we know this outgoing one. So the difference will be what? What happened here, right? So that is low energy. So that's we call Stokes. That means this can be maybe you are, if you had, yeah, this is more like you have, say, it's a phonon. So you have some phonon, that phonon will absorb that energy, right? So that's what, if you look at your spectrum here, this is where this energy difference, right? Energy difference, this h nu minus this one. So in the Rayleigh scattering means nothing changed, that's 0. But in this case, that is decrease, right? Decrease means you will see some change on the negative side. So that's we call the Stokes. But there's something called, so suppose this is my initial state, this is my excited state. Suppose your sample is already excited. That means suppose you have already some phonon there. Then what happens? If it goes here, no, it has to go from here, right? So it's already, this is my excited. Suppose this is already excited state. So if it goes to some virtual state, so then it has to come down here, right? So this is my h cross omega. That means I already have phonon or some process is already happening, it's already in excited state. That means if I had, this is coming at h nu 0, outgoing one will have a large energy, right? Because you had some energy coming from that already excited state. So that means whatever going out has h nu prime, this is actually h nu 0 plus this. This is already excited one, right? That means in this case, if you look at, this is the energy difference. This one I'm talking about, h nu prime. This is what we are, your x-axis is that difference, right? So that, this is your Rayleigh scattering. So this side you had this Stokes one. So this side we have more energy, right? That means you have this side, that's the anti-Stokes one. But typically, if you have already occupied one, so this energy is, this difference is same, right? It doesn't matter this one or what is the other one. If I draw here, this is my original one, this is the excited one. So if I start from here and coming down here, initial and final point, they are the same, right? Here also, this is initial, this is final. That means h cross omega is same. That means you are this anti-Stokes, this one and this one is the same. Only difference is you will find this anti-Stokes peak is very weak compared to Stokes one. Stokes one is much stronger. Why is that? Stokes one, anti-Stokes means already it is in excited state, right? So that means we know that also depends on the temperature, right? Because if you have higher temperature, you have higher gun. So that means you have much lower intensity coming from this outcoming rate. So that's why typically if you look at this way, so this is your Stokes one. So these are strong one, these are, but it's a, if I want to find the temperature of the sample, I can take the ratio between these two. Because this one depends on, highly depend on your temperature, right? Because we know Boltzmann distribution, right? So that depends on your the excitation of the probability of being in that state. So please remember, we never do in this one anti-Stokes because they are too weaker. We mostly looking at the Stokes one. But if I want to get the information about the temperature, somebody has to measure both and take the ratio. So, because this is sometimes very important, because if you are looking at, let's say, nanomaterials, when I shine the light, your sample can get locally very hot. It can be 1000 C because locally we are focusing on to a very fine point, right? 1 micrometer. So that can be really large temperature. So that's, but if you can measure this ratio, you can really calculate that temperature. You cannot locally put the thermometer and measure that temperature. It's a local temperature, right?
Do you calculate the ratio as anti-Stokes over Stokes, or?
Whatever, yeah. Typically, yeah. So if you take intensity of Stokes divided by intensity of anti-Stokes, this goes something like exponential, this whatever your energy over KBT ratio.
Yeah.
You can look at it. Maybe your presentation put
Oh,
that
yeah,
one, that's important, yeah. So from here you can get the, that's the activation behavior, right? You can get the temperature information about that. So please remember, so you have, yeah, this is a good one to show, this one. But here this is a Rayleigh scattering, right? There's no change. Here you have loss of energy because of this, whatever, this one. Here you have more energy. So anti-Stokes means you are already shining light on an excited state, right? It's already in the excited state. That means if you had the phonon already active, you are pretty much annihilating that. That's why people say Stokes is looking at creation of phonons, and anti-Stokes you are looking at annihilation of because phonon is already there, you are pretty much annihilating that. Yeah, so if you look at, this is basically, this is the equation, right? Incoming energy equal outgoing plus or minus this one. If it is plus, it's Stokes. If it is minus, it is anti-Stokes. Right? So then also we know typically momentum conservation. So this is the momentum of your phonon. So typically this Q is, if you look at, so this AI initial and scattered one, you can have either, what is the two limits you can have? If I look at the momentum conservation, if you have Ki, K final or K scattered, the minimum you can have is, the difference can be 0, right? Maximum what can you have? You have to add these two, that can be 2 times K, right? So that's the maximum you can have. So you can have only between these two values, whether it's between 0 and 2K is the maximum. Actually that is, later we will talk about solid state is, that's called the brilliant zone, right? So if you remember, if you have lattice with the lattice constants, probably I cannot remember now. If we have something like with lattice constant A between these two, typically we are talking about the brilliant zone given by this pi over A and minus pi over A. That means 2 pi over A. These are the brilliant zone, right? Depending on this one. So later, if taking solid state physics, we are learning these things in more details. So this is what I was talking about. That's crazy, right? If you don't understand. This is really, these two are equal. So then this is where, so that means this one, nothing happened, there's no vibration, so rotations here, right? Just incoming, outgoing with the same frequency. It's coming here, but because of these vibrations or rotations or anything, so the outgoing light has lower energy or higher energy depending on Stokes or anti-Stokes. This was already vibrating, then this light will make it, outgoing light is higher, right? Because that takes energy from that one. Yeah, please look at this one. So this is actually, Raman, can you imagine when Raman did this experiment, he didn't have lasers, right? He did the experiment, I think, using a hole from the wall in his house, right? So then he focused on to, still he could get very nice Raman.
I think he made a little spectrometer or something.
Yeah,
or
but
something
the
to it,
light
yeah.
to the spectrometer came from a pinhole on
Yeah,
the wall.
yeah.
From sunlight.
Yes.
That's crazy.
So,
Did he use the crystal, like you were saying, to the...
oh yeah, spectrometer had everything. So only to get the light, then he shone it on some kind of liquid. So then scattered light, he had to use the spectrometer. Spectrometers were known right, for centuries, but he could get nice this Raman. So these are, yeah, I don't know, we can go little bit. So when we do this simple the model for atoms, right? If you have some atom that has same mass of your atom in your crystal. So typically if you solve this one, just write the Newton's law and get the typically mx double dot equals minus kx if you move in this direction. So this one moves by this one. Just do this one and put the solution x equals a sine omega t and solve this one. You get the answer for omega, right? So that's very simple to do. If you do that one, what you are getting is simply, you find your omega, the frequency is given by something sine Ka by 2. That means your the omega versus this K is the wave vector. Usually they, something like this. If you take square of this one, then this becomes sine square, right? So then this is, typically this is like pi over A, then minus pi over A sine. This is how we call the phonon dispersion relationship. But, so these are typically we call the acoustic branch, because your omega in this range is linear with K, right? So you can write omega as some C times K. So that's why we call this a acoustic, like long wavelengths. So what if this masses, if you have like 2 atoms per unit cell kind of situation, then you have one atom, say larger mass, and other atom with smaller mass, simple m, and like that. So then this can be complicated, right? You have to write 2 equations, one for mx double dot, then one for m simple mx double dot. Then you have 2 coupled equations. Then you have to take the determinant and solve that one. If you do that one, you get actually omega squared, actually omega 4 equation plus omega squared something equals 0. Then you solve this one, you get 2 solutions. One just like before here, other one comes like this one. So this is still, that's the acoustic branch. This is we call the optical branch. Optical branch means this, that also this can be transverse or longitudinal, right? So transverse means what? If you have these atoms, when the wave is moving, transverse means, so they are moving perpendicular to this one, right? But then also that can be both particles going same direction, or one goes up, one goes down. So same thing longitudinal also, you can have both atoms going like this, or one goes this way, other one goes this way, right? That's why we have this longitudinal and optical, transverse, optical and acoustic. So those things we learned in the solid state physics. But right now, just remember all these things can be seen in the Raman spectroscopy, all the vibrational modes. For example, if I take simple this some perovskite sample, this is what is called some kind of strontium titanium oxide. So this one, so I don't know whether you are familiar with something called the unit cell. So if you take this one has 5 atoms per unit cell. You can count that one actually. If you take all the corner atoms, each corner atom is shared by other 6 atoms from other blocks here, right? That means each one is like 1/6. You have 6 of them. That means you have 1/6 times 6. Then if you take middle one, only one, that's just 1. Then the oxygen atoms are at each surface. That means if you take this one, in the middle of this one, this one, this one, this one, this one, this one, each. So, but each one is connected with another one, right? That means this is shared by 2 surfaces. That means you have 1/2 of each. How many of you have? 6 of them, right? So that means you have how many? You have 1 plus 1 plus 3, you have 5 atoms, right? So typically, if we have 5 atoms per unit cell, so you can have, because of 3, each atom has 3 degrees of freedom, right? That means you can have 15 modes. Yeah. Yeah, 8, that means you have 1 over 8 times 8, yeah. Anyway, it's 1 atom, we know that, right? Yeah. So that means you have each, if you have 3 atoms per unit cell, sorry, 5 atoms per unit cell, we consider the 3 degree of freedom, you can have 15 modes. So from these 15 modes, 3 can be longitude, the acoustic modes. That means 3 means you have 1 in this direction and 2 on other direction. So that means rest should be all optical modes. So optical modes are the ones you can typically see from Raman spectroscopy. So that's, if you look at this one, you can see all these modes. These are transverse optical, longitudinal optical, transverse optical, all these things you can see. Yeah.
What's the unit cell for graphene? Is it 6?
But then unit cell has
Yeah.
2 atoms.
2, okay, so, okay.
So that you can see. So any crystal, you know how to find the number of atoms. In graphene, basically, if you okay. So typically, you can take something like this as your unit cell. That means you have only 2 atoms per unit cell. Okay, I think that's pretty much I want to talk about. So next, let's talk about other things, mostly luminescence. Luminescence is very similar to, so we call the photoluminescence. Also, it can be cathode luminescence or anything, but mostly what we are using is the photoluminescence. In luminescence, what we do is you excite to a high energy level, then when it relaxes, it doesn't come back to the original one, but it comes to a lower one. So that means the rest of the energy will be released as light. So that's how we, so that means you have to excite with, most of the time we excite with like UV light that has high energy, right? So then what is coming out is maybe red light or blue light. So that actually gives you the real, if it's a clean sample, it will directly give you the band gap. Suppose this is my electron here, so I'm going to excite it to higher level, right? But when you, this is my band gap, but I don't exactly give you the, so it can go higher energy, right? So then it will have some collisions and come down to this energy. From there, it's coming down here. During this transition, it is emitting light. Here, I just use this one, say, some initial energy. That's much higher, right? So suppose if I did this one with UV light. So then, what is coming out? Much smaller, right? This can be blue light, or green light, or red light. So that means if you measure this one, you can directly get the information about my bandgap. You cannot excite exactly to this one, right? You go to higher one, but the highest one, they will suffer some collisions. So what will happen during these collisions? Anybody can think
Give
of?
off the momentum.
Yeah, so what will happen to sample? It will heat up, right? Yeah, it's a phonons, right? Yeah. So if you heat it to higher level, when this happens, your sample gets heated. So at the end, it will emit low energy. You will see the different light. So that's how you can get very easily the band gap. So excite with higher energy, and then look at outcome in. I mean, that's the luminous light, right? Typically, if you shine this one with the light, we call it a photoluminescence. But if you shine with some electric field or some other ways, you can excite electrons by different ways, right? You can have some electron beam or some, this is something called the cathode luminescence by beam of electrons, or even some gamma ray, like radio luminescence. So if you use some, so then they can, whatever you have to do is look at what is coming out, right? That's it. But you have to excite to a much higher energy, right? But sometimes if you have some states, so some defect states, right, in the semiconductors, so they might even come here and emit some light before, then it can come from here, then you might see different peak coming, right? That will give information about your even defect states. So those are some details. Yeah. So then fluorescence and phosphorescence, anybody familiar with those things? So fluorescence is basically, if you have, I think you have to look at a little bit about the singlet and triplet states. Everybody familiar with singlet and triplet states in quantum mechanics? So typically, singlet states are if you have two, suppose if you have electron states, so we know they are fermions, right? You cannot have more than, you can have two electrons, right? You have all the quantum numbers same, but spin up and down can be different, right? That means you can have one here, that's fine, right? So typically these are singlet states, but you can have something like, even this is also possible, right? This one, still, that's fine. These are triplet states. So then typically also we know even if you have two electrons, so you know how different ways you can make the triplet states, right? So you can have this way, oh no, so that is singlet state, right? You can make this one, so then you can have this way, or you can have this one plus this one, this one, this one. These are all spin 1, right? They all have spin 1. That's what triplet means. Your spin is 1. Spin is 1. So these are all triplet states. I think in quantum mechanics we all learn these things. Singlet states you can only have typically this one minus this one, right? That's the singlet state. So singlet states are asymmetric. That means if you change one, it becomes negative, right? So but triplet states are symmetric. So if you change, you get the same answer. Please remember that. So if you have these things, actually, you can have this your ground state. So then you can have, suppose your singlet states. First singlet state says 0. Then you can have S1, S2. These are all singlet states I'm talking about. Then also you can have triplet states like this one, right? Typical materials, they form singlet state, right? So most of the atoms, if you take, everything is in singlet state, except there's only one element that is in triplet state, like oxygen, some molecule. So they can be in triplet state. Otherwise, they prefer to be in singlet state because they have low energy, right? So if you have this singlet states, you can have some transition from here to here, right? This is the S0, first singlet state, second, this is second one, right? So, yeah, first state, this is the ground state, S0, singlet ground state. So then you can have, actually you cannot say singlet, this is the ground state. So this is the first singlet excited state, this is the second singlet, this is like the first triplet state. So then you can have transition from ground state to this one, ground state to this one, but you cannot have directly singlet state to triplet state. Please remember that one. So that is forbidden. But you can have transition from here to here and here to here. That's called the crossing. So transition. So if you have, after this one, if you have some relaxation, these are the fluorescence. If you can have relaxation from here to here, that's the phosphorescence. So that's this takes lot longer time. This happens much faster. Like you have seen that glow in the dark kind of thing, right? So those are all phosphorescence, right? That's why they last longer time, yeah. So,
Why is it called phosphorescence?
what's that?
Why is it called phosphorescence? Is that something?
I don't know the origin of that one. They wanted to make difference, fluorescence and.
Something to do with phosphorus?
Yeah, phosphorescence, yeah. So basically, the time scale is the difference, yeah.
Okay.
So if you are talking about even nanoseconds to microsecond to even seconds in the
Yeah.
phosphorescence.
I remember reading a bunch of literature articles.
Yeah.
I'm like, phosphorescent.
Yeah, right.
Does that
Yeah.
have something to do with phosphorus?
You can see because this is a 4-bit one. So here you can see so transition in here. Then but you can have this something. This called the internal conversion between here and even from here to here. Eventually it will come down from here to here. That is the phosphorescence. So here is a nice diagram. You can see this one here. So these are basically the absorptions, right? So these are blue ones are absorption and desorption, whatever. So yeah, this is absorption. These are more like the fluorescence, right? So then, sorry, 3 is the one coming from the crystal state down to, that is the phosphorescence. These relaxations can be any of these, right? It can be vibrational or other. The 6 is the internal conversion. You get that. So these things can be also easily detected by spectroscopy. But this photoluminescence, yeah, as we already discussed about, you can measure the band gap. Yeah. So, luminescence, yeah. Here. So we can see if you measure the fluorescence, not the fluorescence, photoluminescence. Photoluminescence, same equipment we use for the Raman. Exactly, say only difference is you use the UV light. So then you will see, typically if you measure the photoluminescence at room temperature, they are very broad and not much details because you have more population of electrons, right? So, but if you do at much lower temperature, noise is lower, so that means you can get much resolved spectrum because you can see this sample at 220, you can see this peak almost non-existent, right? But if you cool down 190, it's appearing to become so. But if you go to like 6 Kelvin, see how sharp it is. Typically, if you want to get good information, you have to do at much lower temperature. That's what we have something called that Lincoln stage. You can cool it with the. So I don't know whether you have seen that one. Just the attachment. You have to put the sample in that attachment and pump it and pass liquid nitrogen and try to move. But you can use liquid helium also.
Isn't that to like kind of, lower the noise?
Yeah. Lower the noise also. You this way you can see what happens at low temperature, right?
Mm.
You have remember when you excite that one, so it goes to higher level and is relaxing to lower level by collisions, right?
Yeah.
But at lower temperature, so most of the things you can have it here, so that way you don't get too much coming here, right? This is why you get a lot of broad peak. But if it had direct transition from here to at low temperature, then you have much more detail. One is noise and one is like less scattered these transitions. See, low T electrons have less thermal energy, so that makes it, because you don't have that high energy, right? Because already it's cold. This is bad, right? If you try to look at this one, this will first come here, then other ones come little later. That's why you are seeing this broad one. But here, all these things, same time they are relaxing. That means you get sharper. So also we know your KBT noise also lower.
Yeah.
So both of them. So what's the time now?
6:39.
So okay, then we have time. Yeah. So then some linear spectroscopy. So these are, I think, simple things. So we already talked about these things. So then everybody familiar with the plasmon. So typically, if you look at the solve this plasmon thing, so typically what you are going to see is your dielectric constant is given by this 1 minus omega p square, omega square over omega p square. You can easily prove this one. Omega square over omega p square. So you can see if you sweep the frequency, you will see actually this is the real part. Omega epsilon is usually real part plus this imaginary part, right? So see epsilon. So if you look at this is the real part. So this means you will see for omega p is greater than omega, your omega this has positive value. Then if this is less than, it becomes negative value. So this is 0 when omega equals omega p, right? So this is the region you will see your light is passing through the material. It's transparent, right? Here your light is not transparent, can get reflected. So if this is for the epsilon 1. If you measure the reflectivity, you will see here. So at this point, your reflectivity becomes 0. That means every is transparent, right? This one way to measure the plasmon frequency. Just basically shine light and look at the reflectivity, or look at this is hard to measure. Reflectivity is easy to measure. How do you measure the reflectivity?
The intensity of the light.
Yeah, you have the sample, then you have this light coming here, then use a detector to measure outgoing light, right? So just measure as a function of, this one already dispersed light for different colors. You collect the data as a function of lambda, then you can get this reflectance, right? So typically this intensity divided by, that is a reflection, right? So like I said here, you can get that one in more details.
That's surface plasmon resonance sensing.
Yeah. So that if you have this is basically the plasmon from your sample, right?
Yeah.
But if you can modify that one, then you can see that omega p changes. Yeah. So then another important thing you can look at this. This is very frequently what we are doing. If you have, everybody's familiar with something called the direct band gap versus indirect band gap materials. If you have semiconductors, if you look at your band structure, right? You have valence band and the conduction band, right? So if you have these two bands, the maximum of your valence band and the minimum of valence band, conduction band, if they happens at the same momentum, k, so that means you don't need to have any momentum for the energy conservation, right? So your energy is with, you have photon coming here, then if you have this one. But if you have these two at two different positions, so that this is k. So this maximum is here, this minimum is here. So that means your energy is always, this is suppose this energy plus your incoming energy should be equal to this energy, right? That's why you promote it. In terms of the momentum, so this has very small momentum, you can neglect compared to this momentum. But here this momentum and this momentum are equal, because they are same, right? But here this one and this one are different. That means from going from here to here, energy is fine, that is given by this h nu. But for momentum to conserve, for this one you need to add this momentum, right? Then this will be equal. What is this momentum? That will come from the phonons. So that means, when this is the situation, we call that a indirect band gap. This is called a direct band gap. If you want to have a good optical material, you need to have direct band gap. Like gallium arsenide, zinc selenide, these are ideal direct band gap material. That's why they use for photodetectors and all these things. Silicon, germanium, they are good, but they are not direct band gap, they are indirect band gaps. So gallium arsenide, even gallium phosphide, even gallium nitride, these are all very nice direct band gap materials. Silicon, germanium, these are all indirect band gaps. So one way to find, I'll stop here after this one. One way to find the band gap, another way to do is using the UVVs. You just collect your absorption. That's easy, right? With function of lambda. So then if you do this one, you will see something like this. Actually, if it is a direct band gap, it can be shown this alpha as a function of lambda. This is going something like some constant times E minus Eg. Eg is the band gap, square root of this one. If it is the indirect band gap, this is very useful thing. Indirect band gap, this lambda alpha goes something like E minus Eg. Then I said you need to have some phonon coming here, right? But this is very small, you can neglect that one. This goes like the square of this one. Here square root of this is square. That means what you do is you take this one, you just put your sample and change your lambda and measure the absorption. Very simple, right? So if you do this one, then what you do is you just plot. If you this one you can linearize by taking lambda alpha squared, right? Alpha squared equals E minus Eg. Some constant is here, don't worry about that one. That means if I plot alpha squared versus E, you will see something straight line. So where it cuts here is exactly Eg, right? Because when alpha is squared 0, E equals Eg. So simple, right? You just measure the alpha, take the square of that, and with this one you will get the straight line where it is intersecting is directly Eg. But in this case, you have to plot as square root of alpha. Square root of alpha becomes E minus Eg, right? So forget about this one. So in this case, you have to plot square root of alpha and E. From that, you will get your Eg. So this is one way to say whether it's a direct or indirect vector. So here, this is for direct. You have square root of this one. Here you have square root of this one. Okay, so I have like few more slides to talk about. These are all about. So next one I will talk about. So far we talk about optical spectroscopy, right? So maybe I need about 10 minutes to talk about electron and X-ray spectroscopy. So next class, mostly like X-ray photoemission, then ultraviolet photoemission. That's only 10 minutes. Okay, I'll stop here. So then I will quickly talk about the microfabrication, clean room techniques. That's another important thing everybody should know.
Is there like a USB?
What's that?
Is there like, you want to bring our PowerPoint on a USB or like email it to you?
Oh, no, you email
For the
me.
presentation, okay.
Yeah. So then I will put everything here, then, yeah. So please send me, still you have time, right? So
Oh,
next
yeah.
Thursday.
I was getting ready.
You can do it. Maybe everybody's saying,
Yeah.
nervous now. Yeah, better to get over with that one. So that means after next week, you will be mostly working with Dr. Smudgy on the lab, right?
Yeah.
Yes.
Yeah, I was gonna ask you,
Yeah.
so for the
Huh?
presentation,
Yeah.
I'm interested in, talking about the bronze.
Yeah.
But I'm also interested in trying to like calculate
Yeah.
the energy
Yeah.
of the, like, you know.
Yeah, mostly I think you should look at the nucleation kind of thing.
Yeah.
So then how, there are two things, right? The heat flow and the mass flow. Those two are very important. See whether you can get something on that one.
And then I was going
Yeah.
So I was gonna see if I could come to your office and
Yeah.
try and
Energy.
How's your preparation for?
I think that would be useful to have in the
Yeah.
PowerPoint,
Yes.
as well as
Yes,
just
sure, we can discuss it. Monday or something?
Yeah, Monday works. I have to do the optics lab tomorrow.
Yeah.
But Monday morning I
Yeah.
should be available.
Whatever questions you may have.
Yeah, so you guys will turn off light?
Yeah.
I will
Yeah.
do this one.
Yeah. Also studying, planning, whatever.
Okay, thank you.
Oh, yeah, sure.